Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we are going to determine the melting point temperature, the boiling point temperature, and the maximum amount of work that can be harnessed from a chemical reaction solely using thermodynamic data. And so all of this is made possible when a specific condition is fulfilled. And that condition is when the system is in a state of dynamic equilibrium. And so we've come across this term dynamic equilibrium once before when we were beginning to learn about equilibrium. And so if you recall, dynamic equilibrium is a state in which, from our perspective, looking at, for instance, a test tube, it looks like the reaction is complete. And you guys have had some experience with this when you guys were doing precipitation reactions. And so when you mix two solutions and it creates a precipitate, at some point in time, there's no net production of precipitate that's being formed. And so we think that the reaction is done and it's stopped. However, in actuality, when the system is in dynamic equilibrium, when you're looking at the molecules themselves, the reactants are still coming together to form the products, and the products are still reacting together to reform the reactants. And so when the system is in the state of dynamic equilibrium, the change in Gibbs free energy, this thermodynamic quantity, is equal to 0. So this implies that the free energy of the products must be equal to the free energy of the reactants for the change in Gibbs free energy to be equal to 0. And so since we're looking at this delta sign, this is describing a thermodynamic process. And so after the thermodynamic process has been reached, once we've gone from one equilibrium state to the final equilibrium state, there is no net production of free energy. The free energy is equal to 0. And so we can go ahead and use this condition to predict physical properties such as melting point and boiling point. And so I'm abbreviating melting point as MP and boiling point as BP. So we can also use this idea of a system being in dynamic equilibrium to predict the maximum amount of work that can be harnessed from a chemical reaction. So the first thing that I want to discuss or better understand is how can we use thermodynamic quantities to predict, for instance, the boiling point or melting point of a specific substance. And so what we're trying to do is we're trying to understand the connection between these physical properties and in this state of dynamic equilibrium. And so it turns out that if you look at the definition for boiling point is the temperature at which the vapor pressure is in equilibrium with that of the atmospheric pressure. And so because the boiling point is describing the temperature at which an equilibrium has been reached, then it makes sense for us to be able to utilize these thermodynamic quantities to describe or to predict the temperature. And we'll look at a couple of examples in just a second. And so to visualize what's going on in this definition, this idea of vapor pressure and atmospheric pressure being in equilibrium with each other, we have to take a look at, for instance, this idea of a volatile liquid. And so if your liquid is volatile, simply put, it has the ability to access the gas state with very little influence from external factors. And so, for example, if you guys go to the store and buy some rubbing alcohol or hand sanitizer, and if you put like a small drop on your desk or on the counter, at some point in time, you guys will see that that drop completely disappears. Now, it doesn't like magically disappear. It just is converted from liquid to a gas state. And so that's what it means for a substance to be volatile. It can have that, it can gain access to the gas state with very little influence, external influence. And so this state of, or this idea of vapor pressure, so let's go ahead and talk about vapor pressure. And so when your volatile substance goes from liquid to gas state, these molecules that are now gaseous in state is going to impose a pressure on the atmosphere. And so that is what we're referring to when we're talking about vapor pressure. In the same time, the atmosphere is going to impose some type of pressure on the system. So all those gas molecules are the atmospheric pressure is trying to like push it back down to its liquid state. And so the temperature at which both rates of vaporization and condensation is occurring is what's known as the boiling point temperature. Okay. And so here, just to kind of complete the picture, we have atmospheric pressure that's imposing on the system. All right, so in a similar, actually before I move on to melting point, I do want to talk about vapor pressure and atmospheric pressure just a little bit more. And so just imagine that if you somehow influence the system such that the vapor pressure, the rate of the vapor pressure increases, then you have more molecules going from liquid to gas state. So if the vapor pressure is greater than atmospheric pressure, then you should observe bubbles forming. And if the vapor pressure is far, far greater than atmospheric pressure, then you'll see that the solution is going to boil. Now, if it's the other way, if the atmospheric pressure is far, far greater than the vapor pressure, then no boiling will occur, and you'll just see the liquid as a liquid state. Now, it doesn't mean that there's no gas molecules that's being formed. There is, but just not a whole lot. To the point where it forms bubbles. Now, for the melting point temperature, it's a very similar definition. However, the phases that it's referring to is solid and liquid rather than liquid and gas. And so reading this definition, the melting point is the temperature at which the solid and liquid of a pure substance can exist in equilibrium at a defined atmospheric pressure. And so imagine that you guys have an ice cube and you put it in water. And so there's a very, very specific temperature in which the rate of melting is equal to the rate of freezing. And so when these two rates are equal to each other at that specific temperature, that would be the temperature that's considered the melting point. Okay. And so what we're going to do is we're going to learn how to calculate the melting point and boiling point temperature solely by focusing on thermodynamic data. And so you can imagine that this could be something that you guys can do in lab, but for you to determine the melting point and boiling point takes some iterations and so forth and so forth. So sometimes it becomes a little tedious, but anyways, so let's go ahead and look at this example. We're going to go ahead and determine the boiling point of bromine in liquid state in degrees Celsius at 1 atmospheric pressure if the change in enthalpy under standard conditions is 31.0 kilojoules per mole, and the change in entropy under standard conditions is 93.4 joules per mole Kelvin. And so the first thing that I want to do is highlight this term boiling point. And so we have to think about what we're trying to address here. So the boiling point specifically refers to some temperature. And so if we're trying to determine the boiling point, then what we're looking for is temperature. And since we're given two thermodynamic data, enthalpy and entropy, there's only one equation that we've kind of gone through so far that utilizes both enthalpy and entropy, which is the definition for Gibbs free energy. And so here we have the change in Gibbs free energy under standard conditions is equal to the change in enthalpy under standard conditions minus T delta S. Okay. And so if we're trying to look for temperature, then what we're searching for is this guy right here in pink, the arrow in pink. Okay. And so that means all we need to do is plug in the values that this problem gave us into this equation. And so before I do so, I want to draw your attention to the units. Make sure you guys are always writing your units in these types of problems as a reminder for you to make sure that every single number is reflective of the unit and that those units are the same so they can cancel out. Okay. And so for the change in enthalpy, I'm going to go ahead and put in 31.0 kilojoules per mole. And for the change in entropy, I'm going to go ahead and put in 93.4 joules per mole Kelvin. Okay. And so I'm not trying to solve for T just yet. I'm just simply putting my numbers down, right? And so I know that this T is going to serve as my variable, my X that I'm trying to solve for. However, if you look at the problem, it didn't really give us the value for the change in Gibbs free energy under standard conditions. And so excuse me. And so because we are determining the boiling point of bromine gas, the value of delta G naught is very specific. Okay? So if you go back to its definition, it's at the temperature, the boiling point temperature, is describing when the system is at equilibrium. And when the system is at equilibrium, the value of delta G is equal to 0. Okay. And so if you had thought, oh, okay, well, if they didn't give us delta G, I'm going to go ahead and calculate delta G from my Gibbs free energy of formation. In this case, that doesn't hold true, because when we're trying to determine the boiling point, it's implied that the system is at equilibrium. Okay. And so if we just focus on the equation itself, I'm not going to plug in any numbers just yet. So here, the only number I'm going to plug in is 0. And so if the value of delta G is equal to 0, if I just carry down the rest of my terms, and if I want to solve for temperature, then I'm going to go ahead and move this equation such that my temperature is going to be positive and it's by itself. And so what I'm going to do is I'm going to take this guy and move it to the left. And when I do so, I'm going to add the T delta S term. So it's going to be positive T times delta S. And that's going to be equal to the change in enthalpy. And so to solve for T, I'm going to go ahead and divide delta S to the opposite side. And what I get is that temperature is equal to the change in enthalpy over change in entropy under standard conditions. So it's simply a ratio of two thermodynamic quantities, enthalpy and entropy, that's going to give me the boiling point temperature. And so since I am solving for the boiling point temperature, I'm going to go ahead and change the notation. Instead of saying T, I'm going to say TBP. And so this is reminding me that BP is just reminding me that I'm solving for the boiling point. So now that I've reduced my equation, I'm just going to go ahead and plug in my numbers. So my enthalpy value, notice that it's in kilojoules. And so I want to make sure that my units are the same, so I'm going to go ahead and multiply that by 1,000. And so I'm going to get 31,000 joules per mole. Divide this, and if you look at the value for the change in entropy, it's simply going to be 93.4 joules per mole times Kelvin. Okay. Now, when you guys divide these values, your joules per mole is simply going to cancel out, and the unit Kelvin is going to go to the numerator. And so if you're trying to, if you're wondering why the Kelvin goes to the numerator, well, we can simply go ahead and do some fraction work. And so joules per mole is being divided by joules per mole Kelvin. And so if you recall from grade school, when you're dividing these fractions, you guys are going to keep, change, flip. And so what this translates to is joules per mole. We're going to keep that. We're going to change that to a multiplication. We're going to flip the second fraction. And so when you multiply across, these guys cross cancel. And that leaves us with Kelvin in the numerator. And so if I divide my values, they're 31,000 divided by 93.4, that's going to give me 331.905 Kelvin. And so since I'm using rules of division, I'm going to go ahead and just keep to three sig figs. And so here I've kind of expanded this, but this is 31, so that's 3 sig figs. This is 3 sig figs as well. And so right now it looks like there's 2 sig figs, but really this is just 31.0 times 10 to the positive 3. So there's still 3 sig figs in this value. And so what I'm going to do is I'm going to round this to 332 Kelvin. And this would be my boiling point temperature in Kelvin units. Now, if you look at what the question is asking, it's not asking for Kelvin units, it's asking for degrees Celsius. And so I'm going to go ahead and take my answer, my 332 Kelvin, and I'm going to subtract 273.15 from it. And so if I subtract 273.15, I'm going to get 58.7 or 58.8. So it's going to be 58.76. And so since my last operation is a subtraction, I want to be able to keep the correct number of sig figs. So here in this case, I'm going to go ahead and cut this down. So the least number of places after the decimal is directly right after the ones place. And so I'm going to go ahead and round this value to 59 degrees Celsius. And so this is going to be my boiling point temperature for bromine liquid going into gaseous state. So that's cool. I mean, we now are able to calculate the boiling point of liquid. We just calculated the boiling point for bromine liquid into bromine gas, and that temperature is at 59 degrees Celsius. And so what this is telling us is that if our temperature is above the boiling point, so if the temperature is above the boiling point, then that means that our bromine liquid will be converted into gas. And if our temperature is below the boiling point, that means that the equilibrium will lie in favor of the bromine gas. The bromine in liquid state, not gaseous state. Okay. And so this is the temperature at which there's an equilibrium between both phases. All right, so let's go ahead and look at the next problem. So in this scenario, we want to determine the melting point of copper in degrees Fahrenheit at 1 atmospheric pressure if this is the value of our enthalpy and if this is the value of our entropy. And so here we have this chemical equation in which we see an equilibrium between copper solid and copper liquid, which is melted copper. And so once again, if we want to determine the melting point is really just a big fancy name for temperature, right? And so what we're trying to do is determine the temperature if we're given these two thermodynamic pieces of data. Very similar to what we did in the previous problem, we're going to go ahead and use this equation because this equation relates both enthalpy and entropy in one go. And so what we're going to solve for is temperature. However, since we're solving for the melting point, we can go ahead and assume that the change in Gibbs free energy is equal to 0 because this is happening at equilibrium. So this is happening when the system is in a state of dynamic equilibrium, to be more precise. And so once again, we'll see the value of delta G not equal to 0, leaving us with just the standard enthalpy value over minus T times delta S. And so very similar to what I did in the previous example, I'm going to move this term over and then divide both sides by the change in entropy. And so here I'll have T delta S equals to delta H. And so if I were to divide delta S to the other side, I get temperature is equal to the ratio of enthalpy over the ratio of entropy. Sorry, I think I said that. My brain is kind of in automatic mode. So the melting point temperature is equal to the ratio of enthalpy and entropy under standard conditions. All right, and so once again, we're going to go ahead and place the value for enthalpy in the numerator, but we have to convert this into joules. Or if you want, you guys can convert joules to kilojoules. It's your preference. It shouldn't make a difference as long as you converted it correctly. And so for me, I'm just going to go ahead and convert 44.82 into joules. So I'll just say 44.82 times 10 to the positive 3, since I know that a kilo is 1000 or times 10 to the positive 3. That's joules per mole. And then for entropy, it's going to be 33.00 joules per mole Kelvin. Okay. And so when I divide these two values, I am going to get Kelvin in the numerator. And I've shown my work in the previous example. So you can go ahead and refer to that. So I'm going to take these two values and divide them. And what I'm going to get is 1,358. .18. So this is going to be in Kelvin. And so since I need to report 4 sig figs, I'm just going to put a little tick mark right above the first 8 that I see because this is the first 4 significant digits that I see from left to right. And I'm reporting these sig figs for precision. Now, the answer is not asking us, or the question is not asking us to solve it in terms of Kelvin. It's going to be in degrees Fahrenheit. And so what I need to do is convert Kelvin into Celsius, and then Celsius into degrees Fahrenheit. And so the conversion from Kelvin to Celsius is simple. You just subtract 273. So here we have 1358.181 minus 273.15. And so if I put this in my calculator, I'm going to get 1,085. Let me move this over. 0.031. Okay. All right, and now we're in degrees Celsius. Okay. And so we're going to go ahead and take it one step further and convert degrees Celsius into degrees Fahrenheit. And you guys can do so by using this formula, so 1.8 times that by degrees Celsius plus 32. And so whatever our answer is to the correct number of sig figs, which I still need to report 4 sig figs, we're just going to go ahead and plug that value into degrees Celsius. And so here, degrees Fahrenheit is equal to 1.8 times 1085.031, and put that little mark above just to remind me for my sig figs, plus 32. So if I multiply and add, the value that I get is going to be 1,985. So under the provided thermodynamic data, under the given conditions, it looks like the melting point of our copper is going to be 1,985 degrees Fahrenheit. Okay. All right, and so in terms of the math, it's pretty simple, nothing too complex. However, in terms of concept, we have to just remember that melting point and boiling point is describing an equilibrium, a state of dynamic equilibrium. And so when your system is in dynamic equilibrium, you can go ahead and make this assumption such that delta G equals to 0. Okay. All right, and so hopefully that clarifies how to calculate the melting point and boiling point temperature based solely on thermodynamic data. So that's pretty awesome. So we no longer really have to go into lab if we know the value for enthalpy and entropy, just to calculate the melting point temperature and boiling point temperature at a specific pressure. Now, these values will change if pressure changes. And so that relationship can be described by looking at a phase diagram, which hopefully you guys were introduced to in the first semester of general chemistry. And so if you guys don't know what a phase diagram looks like, I think I drew it over here. So this is the phase diagram of water. So this phase diagram is simply describing the combination of pressure and temperature to produce a physical, and the outcome of the combination of pressure and temperature would dictate the physical state of matter for that substance. So for example, if you have low temperature, so think about things that are cold, and if there's high pressure, then if you connect these two, it's predicted that your substance will be solid in physical state. And so these lines, the ones that are in pink, blue, and brown, they are representing phase boundaries. And so the phase boundary is literally the melting point or boiling point. So what I'm putting dots on is between solid to liquid. So this is representing the melting point. So notice how the melting point temperature changes per varying pressure. So it's not like a uniform line, it's kind of slanted downwards. And so as we increase pressure, so to speak, the melting point temperature also decreases. Okay. And so this phase diagram is specific to water. The phase diagram for all other substances are going to be different than water, than what you guys see. And so this phase boundary is going to describe all of the potential boiling points, all the temperature that would describe the boiling points. And it varies when pressure changes. So if when the pressure increases, notice that the boiling point continuously increase. Okay. All right, so the next thing that I'm going to discuss, is the relationship between the Gibbs free energy and that of the maximum amount of work that can be performed or the maximum amount of work that can be harnessed from a chemical system or chemical reaction. And so let's go ahead and think about like this extreme case. So if a chemical reaction was performed, all of the free energy, let's just say it's an exergonic reaction, all of that free energy that was produced from a spontaneous reaction could theoretically be used to do work. And so this is telling us that the maximum amount of work is equal to the total free energy. So all of the free energy that's produced from a spontaneous reaction could be used to do work. So therefore, the change in Gibbs free energy in an exergonic reaction is proportional to the maximum amount of work that can be done by the system. And so this condition is only true for reversible reactions. And we'll talk about this idea of reversible reactions or reversible things that are reversible versus irreversible. And so let's go ahead and look at this system right here. So this is a piston. So imagine that we're referring to a specific component in an engine. And so inside your engine, you have like this movable piston, and inside a combustion reaction will occur. Okay. And so when a combustion reaction occurs, it's going to move this piston upward. And since this is connected to something else, that whatever it's connected to is going to allow your vehicle to move in the forward direction, right? So this is going to allow the car to go forward when you step on the gas. And so there, how do I say this? And so when a combustion reaction occurs, the piston is going to move upwards. Now, when that piston moves upwards, not all of the energy that was released from the chemical reaction is actually going to, so not all of the energy that was released from this combustion reaction is going to be used to, it's not going to be used to perform work, right? Some of that energy from the combustion reaction is going to be released as heat. Okay. And so that would be the scenario for irreversible processes, right? And so when you're talking about reversible reactions, for all of the energy from a combustion reaction to be used for work, that means that there needs to be an infinitesimal change in the volume of this system. So in other words, when this combustion reaction occurs, for all of that energy from the combustion reaction to be used for work, the change itself must be infinitesimal, such that it's reversible. And so the idea is that if you move this just ever so slightly upwards, and that is like a little small arrow that I just drew. So I'm going to erase some arrows here. And so the idea is that if you slightly increase that piston ever so small, ever infinitesimally, like super, super small, then you can achieve this the state where all of that energy that was produced from the chemical reaction will be used to perform work. In other words, none of that energy is going to be released as heat. Okay. And so this idea of infinitesimal changes really can only occur when you have a reversible reaction. And when you have a reversible reaction, technically you are going to be in this state of dynamic equilibrium. Okay. And so I guess to clarify this idea of infinitesimal change and work, imagine yourself in your room, and your door is closed. And so if you wanted to open your door, and if all of the energy that you're going to invest in opening that door is going to be used to perform work, and that is opening your door, and you don't want any of that energy to be lost as heat, what you want to do is you want to slowly, like very infinitesimally, open your door. And so that infinitesimal change is so, so, so small that in the broad scope of things, it's going to take you a long, long, long time to open your door, which is not very feasible in the world that we live in. And so this idea of being able to use all of the energy from a chemical reaction to perform work is not feasible in the real world. Okay, most of, and so I was supposed to put in dynamic equilibrium here. I'll explain this. I'll come back to this point in just a second. So most of the processes that occur in the real world are irreversible. So when you open that door, the energy that's invested in opening that door, not all of it is going to be used for work. Most of it, or some of it, will be released as heat. And so the reason why it's favorable in one perspective in terms of thermodynamics is that when we open the door, when we release heat, when part of that energy invested is released as heat, we're increasing the entropy of the universe, of the surrounding, right? And that increase in entropy follows very favorably according to the second law of thermodynamics. Okay. And so for this infinitesimal change to occur, the reaction itself, or the system itself, must be in dynamic equilibrium so that it can easily and quickly be reversible, right? And so if you imagine yourself, really having this large change in this piston, the work that was performed, most of it, or some of it, will be lost as heat. Okay. However, when you have very infinitesimal changes, in this example, all of the free energy that was released by the system can be used to do work. Okay. And so under this idea of dynamic equilibrium, the change in Gibbs free energy is going to be 0. And so once again, theoretically, reversible processes enable us to utilize all of the energy that was produced to do work. In other words, no energy is lost as heat. And unfortunately, all real processes are irreversible. Okay. So in the real world, like when you step on the gas in your gas pedal, the combustion reaction that's occurring inside your engine is irreversible, right? It's once that reaction has gone to completion, some of that energy will be used to perform work, but some of that energy will be lost as heat, okay? Which once again abides to this idea of an increase in entropy, as stated in the laws of thermodynamics. And so when you guys are looking at this equation where we have the change in internal energy, so this internal energy is the amount of energy that the system has. When you move the terms around, the work that's performed through irreversible reactions can be calculated by the change in internal energy minus the amount of heat lost to the surroundings. And so whatever you're left with when you subtract these two values, that's how much energy can be used to perform work. In other words, the work performed by irreversible reactions is always less than the theoretical amount of energy possible to do work. Okay. And so, when we're talking about like creating an engine that's sufficient, self-sufficient, for example, a perpetual motion, an engine that is moving in perpetually, it's impossible to create that because not all of that energy will be used to do work, to create that perpetual motion for that machine. As work is being performed, heat is always a byproduct of work for irreversible reactions. Okay. And so there are some ways to increase the efficiency to ensure that, to kind of boost the amount of energy that we can, use to do work by, for example, like coupling a spontaneous reaction to a non-spontaneous reaction many times over, right? And so for those who are going into engineering, this idea of creating an efficient machine, being able to utilize as much energy possible from that source of fuel is always going to be a great interest in that industry. Okay. All right, so let's go ahead and go back down to chemistry. Here we're going to go ahead and look at just one example of how to calculate the theoretical maximum energy that can be harnessed for work, that can be harnessed as work from a chemical reaction. And so here we have this substance. It's solid in state, so it's oxalic acid in solid state. And we're going to go ahead and perform a combustion reaction. And we know that we have a combustion reaction because we produce, our second reactant is oxygen, and we produce CO2 and water vapor. Okay. And so if the combustion, so what we want to do is we want to calculate the theoretical maximum. What's the maximum amount of energy that can be harvested or harnessed for work from the combustion of oxalic acid from its solid form. And so here we are given our thermodynamic data, enthalpy and entropy. And so all we're going to do is we are going to use this equation and simply plug our numbers in. When we plug our numbers in, we want to make sure that our units match up. And so here we have negative 246.1 times 10 to the positive 3 joules per mole, minus that by temperature. And so if you guys read this problem, notice that temperature was not indicated. However, we know that we're in standard state, so we're going to go ahead and assume that temperature is 25 degrees Celsius. So in terms of Kelvin, that's going to be 298.15. And so entropy is given to us as 377.1 joules per mole Kelvin. And so the kelvins will cancel in this scenario, just leaving us with joules per mole. And so if you guys calculate this out, So this is negative 246.1 times 10 to the positive 3. So I'm just going to go ahead and put in my calculator. 298.15 times this by 377.1. The value that I'm going to get is negative 3.585 times 10 to the positive 5. This is going to be joules per mole. And once again, I can go ahead and express this value in kilojoules by extracting it times 10 to the positive 3 from times 10 to the positive 5. So I'm going to break it down into times 10 to the positive 2 and times 10 to the positive 3. And this guy becomes the kilo in the joules. And if I were to expand this, I'm going to move this decimal place 2 places to the left. So that will express the times 10 to the positive 2. So really I have negative 358.5 kilojoules per mole. And so this is going to be, this value right here, it's going to represent G max. Okay. This is going to represent the maximum amount of free energy that was released from the reaction. But that's not what the question is asking us. It's not asking us to figure out the free energy. It's asking us the maximum amount of energy that can be harnessed as work. And so what we're going to do is we're going to take this value, right, and we're just going to simply change the sign to represent max work. And so by flipping the sign, this is going to inform us of the maximum work that could be harnessed to do work. Excuse me, sorry. And that's pretty much it. All right. So hopefully you guys understood some of the basic concepts with respect to applying this idea of a system being in dynamic equilibrium to calculate the boiling point temperature, the melting point temperature, and being able to calculate the maximum amount of work based on the value of the Gibbs free energy. All right, so we're going to go ahead and extend this topic a little bit more in the next lecture video. See you guys.